Welcome to this week's SPCL VCast. We are again extremely happy to have a leader in industry, Karthik Kashinath, who's going to tell us about the digital twins, something that is very dear to our heart here at SPCL. We're also working on related things, and I'll let Nikolai introduce him.
Thank you, Torsten, and thank you again, Karthik, for agreeing to come in and give a talk here. Karthik is a senior machine learning scientist and technologist at NVIDIA, where he leads various machine learning initiatives for Earth system science and computational fluid dynamics, including the Earth-2 initiative. Before NVIDIA, he was at NERSC and Lawrence Berkeley National Lab in the US, where he led a number of initiatives on climate informatics, machine learning, and so on. He received his bachelor's from the Indian Institute of Technology, Madras, a master's from Stanford, and a PhD from the University of Cambridge. His background is in engineering and applied physics. And among his other side interests is cooking up a storm, which is very relevant to what he will be talking about here. And with that, Karthik, please go ahead. Thank you again.
Thank you for the kind introduction, and thank you for the invitation to present. I'm really excited to share with you some of the recent work that we've been doing here at NVIDIA with the Earth-2 initiative. And as Torsten mentioned, it's an exciting time for digital twins and the idea of using AI to build these digital replicas of various different physical systems, not just the Earth, but biological systems, engineering systems, and so on. Okay, so I'll get started with a little bit of context on why climate science needs digital twins, how machine learning can offer some exciting opportunities and what the challenges are, and then finally get into a little more detail on a particular model called FourCastNet that we've been developing here at NVIDIA in collaboration with several others, which is a step towards building a digital twin of the Earth. So the challenge is probably clear to all of us. Climate change is here and now. It's happening across the globe. We see the impacts every day. There's a dramatic rise in extreme weather events across the globe, and many of these have been attributed to climate change, in particular their amplification and changing patterns. Just looking at a snapshot across the globe, we have wildfires in California and Australia and elsewhere, mudslides and various other extreme flooding events simultaneously, drought in other parts of the world, multi-year droughts that are getting worse. And again, floods happening simultaneously in other places. And here again, an example of drought. So we have basically extremes of all kinds: heat waves, cold waves, droughts, extreme flooding events, etc., happening simultaneously across the globe. And this is a snapshot of just one particular season, the summer of 2021. And we have here a depiction of the different types of extreme events. And we see that it is a global trend, and no place, no continent is really free from these extremes. And of course, down here in Antarctica, we're seeing some pretty catastrophic changes to the ice sheets as well. So just to set the stage for why we need AI and digital twins in climate science has been progressing in terms of modeling over several decades. Increasing the spatial and temporal scale of these models has been the trend and continues to be the trend. This figure here is adapted from Tapio Schneider and Chris Berthetton and others from a recent paper in Nature, where they basically show the way in which resolution has changed over time. And here we're having the various different IPCC models. And today we're looking at, in fact, with the CSCS model, ALPS coming up soon. In 2023, the target from Thomas Schultes and others is to have a 1 kilometer model running at 1 SYPD, 1 simulated year per day. So if we take that as our sort of baseline, which is convection resolving at 1 kilometer scale, and project forwards in time, at 100-meter resolution, we would need 10,000x compute, because compute scales with resolution to the fourth. And at that scale, we're starting to resolve the fine scale details of storms. But really, to get to the holy grail, which is stratocumulus low clouds, which have a huge impact on climate uncertainty, we would need something like a meter resolution, and that's 100 billionx more compute than we have today. And based on current computing trends, we're looking at 2060 to be able to actually get to that resolution. And that might be too late for us to address the pressing questions of climate change. Simultaneously, the constraints on the size of ensembles and scenarios are also severe. Right now, we have ensembles that are order of 10 members. ECMWF has the 51-member ensemble, but we really need members, large ensembles with thousands of members to be able to characterize the uncertainties in the tails of the distribution, that is extreme events with higher confidence. And on the climate side, we're also looking at scenarios for different types of projections towards climate change. And we do have a deck of scenarios that are probably order of tens of scenarios, but we know that we could potentially be exploring thousands of scenarios, and that would, of course, require much larger compute. So how do we address this question of very severe computing demands to be able to actually characterize climate change more accurately and predict impacts? So advances in computing and machine learning are starting to promise some really massive speedups. And on the left is just a cartoon that shows how accelerated computing using GPUs and other technologies at data center scale is starting to give us the sort of rapid increase in computational speed up, and simultaneously machine learning and AI is also giving us a very rapid increase in speed up. So combining these technologies together, we perhaps have a chance at making this giant leap of 1 million x speed up, which is really the exciting challenge that we have here today. So the Destination Earth, which is the European Commission's 7 to 10 year project, sort of lays out a vision for what the future of Earth system modeling could be. And they basically coined the concept of digital twin Earth and describe what it would take to realize this. So the sort of 5 key elements that are needed to realize digital twins are, first of all, to have an intuitive user interface where you can actually ask these what if questions and have rapid answers, sort of a sim Earth type of thing. Data-driven models are recognized as a pretty important key aspect of this, and we'll get into some more details on that. Storm resolving models, so very high resolution of process-based physical models are also an important ingredient. Observations of different kinds, unifying them. So we know that we have observations coming in from hundreds of different sources and maybe even unconventional sources like IoT. And then finally, the obvious need for exascale compute. So NVIDIA looked at this and said, okay, well, we have some of the technologies that are needed to make this a reality. So why don't we go after the problem? And just to describe some of the work that's going on, Omniverse is one of the technologies that's being used to develop these interactive user interfaces that are intuitive, that allow collaboration and so on. There's a framework that we're building, which is a combination of physics and machine learning. So to build physics-informed machine learning models called Modulus. There's, of course, GPU acceleration of these models that are happening and have been going on for quite a while now. The Omniverse nucleus provides an opportunity to unify observations of different kinds, different data sources, and so on. And finally, exascale compute with the next generation of systems, the Omniverse SuperPod and future generations. So Earth-2 is this project that was launched by our CEO, Jensen Huang, about, I'd say 5-6 months ago at the GTC fall last year. And the question is, why do we need this Earth-2 digital twin? Well, it is to achieve essentially what Destiny has laid out, which is interactivity at scale, to be able to really unfold and extract the information that exists in climate data to make it actionable and to make it actionable in actionable time, so meaning fairly soon. And how do we do this? Well, the process is to build these digital twins that can be used to monitor, predict, mitigate, and adapt to various different scenarios. And there's more descriptions of the vision in the link at the bottom. So just to give a cartoon of what a digital twin looks like, so we have data coming in from different sources. On the right are simulations, so physical simulations governed by the equations describing the system, very high resolution. This provides synthetic data. This allows us to explore different scenarios, different conditions, and so on to generate a very large data set. And simultaneously, we have observations coming in from the left. So physical observations from satellites, sensors of different kinds from the land, the atmosphere, ocean, sea ice, et cetera. And that gives us sort of the real data from the physical world. This data can be fused together and then used to train either a single deep learning model or a whole suite, a system of deep learning models for different purposes. And that combined together gives us essentially a digital twin that can be used in inference mode to predict scenarios, to predict the future of climate change, but also extremes, impacts, and so on. And of course, the digital twin is not a sort of one-time shot. It's an iterative process. So once you train a digital twin, you can run new simulations to gather more data of specific scenarios where you probably don't have enough characterization. You might also control the way in which new observations are gathered from the actual physical system. So you might be able to control sensors and satellites and so on. And so this continues in an iterative fashion, continuously recalibrating and retraining and optimizing as it goes on. So one of the ways in which a digital twin can be used for sort of impacts is to couple it together. So you have multiple data-driven models that are coupled together within the digital twin to give you results that society cares about. So you might start off with a climate digital twin that emulates the climate system and can project into, say, the future, say 10 or 50 years ahead. And under that scenario, you might be able to initialize a weather digital twin that takes in conditions from the climate digital twin to run very targeted short-range projections. And then you can use that to characterize things like extremes. And that can be fed into something like power plant digital twins to capture the fluctuations in energy production and so on. And that can be then fed into an electric grid model to characterize the vulnerabilities. So this is just one example of a way in which it could be used. Of course, this is the vision. We're not quite there yet, but we're building up towards it. So I'll dive into some of the, maybe the most exciting part for me, which is the machine learning challenges and approaches that we can use to solve this problem. So starting off with the challenges in climate change and extreme weather in general, of course, we're looking at an extrapolation problem here. So this is a non-stationary system. The climate is changing as we speak, and that requires us to extrapolate into futures that have never been seen before. And really, the only way we can do this is using the physics, because physical laws extrapolate, whereas machine learning models don't necessarily do that very well. And then that directly relates to the question of physical consistency and causality. A lot of these data-driven models are not necessarily physically consistent and causal models. And we need to embed some of the physics into these models and come up with clever ways of enforcing causality as well. Uncertainty quantification and calibration is a big one. This remains a grand challenge for us in climate modeling, but also in the case of data-driven machine learning models. Data fusion and assimilation is starting to become a really exciting and important challenge given the multiple different data sources and just the volumes at which data are coming in. And there are some promising ways in which machine learning could help address that as well. And then finally, scaling up and scaling out to getting to extremely high resolutions and extremely large scale. So some of the approaches that have been explored in the community and also here at NVIDIA in using machine learning to address these challenges is emulation. So emulation of the entire global system, an entire weather system or climate system, but also emulation of specific processes. So things like machine learning emulators of radiation, convection, and so on. Super resolution, also known as downscaling in the weather and climate community, is another area that's actively being explored. Very important for impacts to really predict variables and metrics at fine scales where people live and the impacts matter. Segmentation, which is essentially detecting features like tropical cyclones or extratropical cyclones, atmospheric rivers, other types of weather events, and tracking them in space and time. Online learning is a big requirement for digital twins because we need to continuously recalibrate our model as we get new data, new simulations, and so on. And finally, something that's relatively unexplored, which is reinforcement learning. And one of the ways in which we could use this in a digital twin setting is to have the system automatically using a reinforcement learning algorithm to discover new mitigation and adaptation strategies that humans haven't discovered before. So there's many exciting opportunities, and I just want to show a video of Omniverse where we have segmentation of extreme weather events. This is work in collaboration actually with folks at ETH, Andre and Lucas, and also some folks at UC Berkeley and Lawrence Berkeley Lab. And this is a 3D segmentation of extreme weather events visualized in Omniverse, the interactive visualization platform. And here we're looking at extremes in the year 2100. This is segmentation done on climate data from a simulation. And the model is trained to essentially detect and track in 3 dimensions in space and time these extreme weather phenomena. So these deep learning tools that have been developed in computer vision can be adapted for physical science applications in very reliable ways. And there's a paper that describes some of this work in more detail. This won't be the focus of my talk, but I just wanted to sort of show you what the types of applications are. I'd like to dive into what are the specific steps that we're taking towards building a digital twin. And it's called FourCastNet. It's a model that was developed over the last year or so here at NVIDIA in collaboration with others. And it's a global data-driven high-resolution Earth digital twin for extreme weather. So the team consists of several folks from NVIDIA, from Lawrence Berkeley, from Caltech, and a few other universities. And it's really a nice collaboration of domain scientists with computer scientists, machine learning experts, and also folks on the computing side to scale this out to large scales. So I want to briefly introduce the machine learning approach that we use here, which is different from kind of the range of different approaches that have come up in deep learning over the years. So of course, we're all familiar with neural networks and what they do, functional mappings in finite dimensions. So that's depicted here on the left. And the approach that we use here is called a neural operator, which is slightly different in the sense that it maps between infinite dimensions. So it's mapping between function spaces. And what that means is that we can essentially learn operators between continuous inputs and outputs. And this is very powerful for physical systems that are governed by partial differential equations because we can learn the underlying dynamics of a family of PDEs. The other properties of this approach are that it can be used to basically data from multiple different sources, whether it's simulations or observations, and also spanning orders of magnitude, different scales in space and time, coming from different grids, so different resolutions, different structures, and so on. So it's a nice way of combining data from basically multiple disparate sources into a single model to learn the underlying dynamics of the system. So the mechanics of how this works is quite similar to a neural network, a standard neural networks like a CNN, but there's a few key differences. You have your input coefficient functions, and instead of having convolutional operators like in a CNN with filters, you replace that with a Fourier layer. And what the Fourier layer does is it takes a Fourier transform of the data, does operations, linear operations in Fourier space, and then you take the inverse Fourier transform. And then you feed that through a nonlinearity as you would in a standard neural network. So it's a composition of linear and nonlinear operations. And then this basically comprises a single Fourier layer. You stack those together to create basically a Fourier neural network with Fourier neural operator network with multiple such Fourier layers to ultimately get your outputs. The key advantage of using the Fourier transform is that you achieve global convolutions. So you have correlations essentially across all scales in space and time that are captured. It's very efficient because you can do this with essentially a handful of modes. In our model, we have something like 64 modes to capture basically the entire range of spatial and temporal correlations. You learn the entire solution operator of the system. So you're learning the underlying dynamics of the PDE system. Of course, we know that the weather and climate system has more than just PDEs, but the solution operator of those systems are also captured. And finally, it's continuous mesh independent and resolution invariant. So that allows you to work with different data sources. So we've extended this approach to combine it with transformers for a few different reasons. It's computationally efficient, and it also allows us to leverage the power of transformers, which of course are all the rage right now in deep learning. So it allows us to do efficient self-attention, basically using the FNO. So here we're just showing one transformer block, and more details are in this paper here below. We have the patch and position embedding, which is the standard sort of transformer first layer, and then the spatial mixing is done using the FNO. So we have basically FFT-based global convolutions. And the AFNO has certain key advantages in that it does efficient token mixing, by breaking up this into blocks. So you have block channel mixing and adaptive weight sharing. So there's a lot of computational advantages to using the AFNO over the FNO in this case. So in our case here, for the application for FourCastNet, we use this particular model, the AFNO, which combines the FNO with transformers. And this is a much more scalable model than the FNO itself. So I'll dive into a bit of the training details and then get into some of the results and scaling and computational challenges. So here on the left shows the entire process in a nutshell. So we have data coming in from the Earth-2 dataset, which is a reanalysis dataset. And for those of you that are not in sort of the weather and climate space, it's basically the best representation of reality that we have, which combines observations with a numerical model. And it goes back to 1979. So we have about 45 years of data at this point. It's at a resolution of 0.25 degrees, which is about 30 kilometers at the equator. So we use that resolution at the native resolution. The variables that we train are about 20 variables coming from surface variables, so velocities at the surface, temperature, pressure, and also various other variables at different levels in the atmosphere. So as we go up into the atmosphere, we have velocities, geopotential heights, relative humidities, which captures the moist processes, and also the total column water vapor. So we're in the process of extending this model out. One of the nice things about the scalability is that we can increase the data sizes. So we're including radiation, vapor transport, clouds, and so on. So the training set was from 1979 to 2015, and that gives us about 50,000 training samples. We validate and tune our hyperparameters on 2016 and 17, and then we have a held out test set from 2018 onwards to evaluate the performance of the model. So getting a little bit more into the mechanics, the model is set up in a way where we take inputs at a given time step t, or in this case, k. So we have a full state vector here in space of all the different variables, and we predict the same variables on the same grid at the future time step k+1. We calculate one loss at that instant, but we then run the model once again auto-regressively to predict the next time step and calculate a second loss. So we're optimizing over essentially 2 time steps here. The second part of the model is that we have a diagnostic model for precipitation. So precipitation is sort of a complex variable that depends on essentially all of the prognostic variables. So we have a backbone, which is our main model, which predicts the prognostic variables, and then precipitation is a separate model, which has the same structure as the FNO backbone model, and it predicts the precipitation at that time step. And then we, of course, calculate a loss for that too. So once the model is trained in inference, we can basically feed in inputs and get the predicted prognostic variables at the next time step, and then put it through the precip model to get the precip at that time step. Right, so that's the framework of the model, and I'm happy to discuss more details in the Q&A. I'll describe some of the results that we have here. So first of all, we have very good results on fast timescale variables, so things that have very fine scales in both space and time, and this has always been a challenge for deep learning approaches. There are many models out there that have predicted the large scale dynamics at low resolution, like 5 degrees or 3 degrees fairly well, but capturing the fine scales, which are important for things like extremes and impacts, has been a grand challenge. So here we're seeing predictions at 25 kilometer resolution, the native resolution, and we're looking at surface wind speeds. On the top is the initial conditions across the entire globe. We look at 2 insets. So at the bottom are the predictions 4 days ahead, and focusing on these insets. So the one on the left is focusing on the West Pacific off the coast of China and Japan. And we see here that 4 days later, there's the formation of this large typhoon, Typhoon Mangkhut, which actually had massive devastation across the coast of China. And our model is able to capture the formation of that typhoon and also the spatiotemporal dynamics of that typhoon fairly accurately. The large scale wind patterns are captured well. And as you can see, there's some fine scale structure that is not so well captured, which is something that we're working on. So on the right is results in the Atlantic. So we see here the formation of these tropical storms off the coast of Africa heading towards the United States. And 4 days later, we have the series of hurricanes Florence, Isaac, and Helen that are well formed here and all heading towards the east coast of the US. And these are captured well as well in the model. So what we're seeing here is that complex fields with fine scales like winds are being captured well globally, and also the extremes associated with those. So focusing on one particular hurricane here, we have on the left the predicted hurricane track and the forecast, the actual hurricane track and the forecast from our model. In red is our forecast mean, the ensemble mean. The ellipses show the uncertainty bands over the ensemble, and in blue is the actual track. One of the nice things about this model is that you can run this essentially in a fraction of a second in inference, so it's orders of magnitude faster than a numerical model, which allows us to generate large ensembles. So we can generate a 1,000-member ensemble in a few seconds, and that allows us to characterize essentially uncertainties very quickly. On the right, we're seeing the actual spatial temporal dynamics recorded in the 850 hectopascal wind speeds. And once again, as we saw in the previous figure, we're capturing the spatial temporal evolution of this hurricane quite well over this period of time. So I'd like to show a video of what the predictions look like in Omniverse, which is our platform for visualizing and interacting with the data. So we're looking here at the predictions of essentially all these variables across the globe, and we focus on solid contours, which is the ground truth, and the filled contours, the open contours, which is the predictions from our model. And we're looking here at a particular hurricane in the Atlantic. I think it was Hurricane Matthew, which had devastating impacts in Florida. And we see that the model is capturing the essentially the spatial temporal pattern of the hurricane and the evolution and the track pretty much accurately all the way through the entire duration of the hurricane here. So that's quite promising in terms of capturing the dynamics of these events. So moving on to maybe the holy grail in weather and climate modeling, which is precipitation, one of the most complex variables to predict at fine scales. On the left is the accuracy of the forecasts, just to orient you. On the x-axis is time, and on the y-axis is ACC, which is the anomaly correlation coefficient. It's the measure of skill. ACC of 1 is perfect, and ACC of 0 is not so good. And of course, as we move forward in forecast time, the skill decreases. In red is our FourCastNet model, the data-driven model that we built, and in blue is the IFS, which is the state-of-the-art for weather forecasting. And we're seeing that we're actually beating the IFS at short timescales and comparable to the IFS at longer timescales on precipitation forecasts. There's a couple of caveats here. First of all, our resolution is lower, so IFS can run at 9 kilometers, we're at 25 kilometers. And then we're not using observational diagnostics here to evaluate the performance. So that's something that we're working on right now. On the right shows you the actual spatial temporal fields of precipitation across the globe. Once again, the initial conditions are on the top, and then the predictions in the middle, and the ground truth on the bottom. If we just take a quick glance at this, we see that the patterns of precip are captured pretty much accurately throughout the globe. There's fine scale details that are missing, but if we zoom into a couple of regions of the globe, so on the left, we're zooming into North America, and in particular, we're focusing on the West Coast here. There's a large atmospheric river that's making landfall along the West Coast, and we see that our predictions are pretty much spot on with the ground truth. On the right, similarly focusing on Western Europe and the UK, we have this large extratropical cyclone that's predicted, which is also very similar to the actual ground truth. So once again, we're capturing precipitation patterns quite nicely globally at relatively fine scales. So here we see the full dynamics predicted over, I think, a 5-day period. And we're looking at, in this case, water vapor. So the total moisture in the atmosphere integrated from the surface to the top of the atmosphere. It's a very good marker for weather patterns and the dynamics of the atmosphere. And if you maybe spend a few seconds looking at the video, on the top is the prediction, on the bottom is the ground truth, and you'll see that the dynamics are being captured nicely, the formation of these large atmospheric rivers, extratropical cyclones, and so on. On the right is an inset that shows a particular atmospheric river making landfall in California. Okay, so I think in the interest of time, I'm going to skip this other video, which also shows the dynamics, but I think probably the story is clear that the spatial temporal systems are being captured nicely, and I'll get into some more details on the quantitative results. I do want to make one remark on the implications for, besides extreme weather, also for wind energy planning. We do have excellent predictions on surface wind fields across land, across the United States, and the same is true for other parts of the globe. And here we're seeing over a 3-day period, and the forecast actually continues on beyond that. We're capturing the winds, and especially the high wind regions and the patterns of winds quite well, which actually is quite important for wind energy planning and estimating the power up and so on of wind farms. So this could be a very useful model for renewable energy as well. Looking at the performance on extremes, and I do want to remark here the challenge with the fine scale details is because we are missing some of the fine scale features, we do not get the extremes at the highest percentiles quite accurately predicted, although we are approaching IFS. So here we're looking at precipitation on the left side, and on the right side is winds. And we see here basically all the way from the 90th percentile to the 99.9th percentile, FourCastNet is lagging behind IFS in terms of the extremes. On winds, we seem to be doing a slightly better job than on total precipitation, but this is something that I think is work that needs to be done in capturing the fine scales more accurately. So just to maybe show a few different variables that are important for impacts besides precipitation are the winds, the geopotential height at 500 hectopascals. This is a very important variable for the dynamics of weather patterns. And then finally, temperature, which is of course relevant for heat waves and droughts and so on. And in all three cases, we're seeing that our model in red is doing really well at short time scales, and then it starts to lag behind IFS in blue at longer time scales. But it's quite remarkable that a data-driven model that basically has been trained over about 40 years of data is already approaching operational weather forecasting, maybe about 24 hours behind in terms of skill. But it seems to be doing quite well across multiple different variables. So I don't want to compare against the state of the art. So of course, people have been using deep learning approaches for weather forecasting over the last couple of years, and there's been at least 4 or 5 models that have come out in this period of time. And the sort of benchmark for us is what was the state of the art before our model, and I would consider ours as the state of the art at this point, was from WEYN et al. In 2020 from the University of Washington and some collaborations with Microsoft. And they had this model which was based on a UNet architecture with CNNs, and this is their forecast skill in black, and ours in red, and blue is the IFS. So we're seeing that using these new approaches like the Fourier Neural Operator, along with transformers, we're able to essentially push the prediction horizon further and also get better skill and accuracy, including at fine scales. So shifting gears a bit to the computational performance of this model, which I think is actually very, very exciting and perhaps very interesting for us here as we think about the computing side of these things and the implications. Given the speed of this model, we can basically run a 100-member ensemble forecast in 7 seconds on a single node. And this is 4 to 5 orders of magnitude faster than traditional numerical weather prediction. So we're already approaching NWP in terms of skill, and we're 4 to 5 orders of magnitude faster. And this has huge implications for extremes, for being able to simulate multiple scenarios, characterize the confidence of the tails of the distribution, and so on. But also interesting is that this 100-member ensemble consumes about 4 orders of magnitude smaller energy to produce this forecast. And I think that's important as we start to move towards building a digital twin of climate, that we do think about energy efficient ways to do this. It would be ironic if we had to basically put out a bunch of carbon into the atmosphere in order to predict the atmosphere. So it's good to note that the model is also very energy efficient. There are a couple of caveats which we're working on, which is that currently FourCastNet is not physics constrained, which means that it doesn't have any embedded equations or other constraints. But this is something where we already have techniques to do this. There's a whole body of work in physics-informed machine learning, which I actually have been contributing to. And there's some nice ways to include physics into this model. And then the second, of course, on the computational side and also for impacts is to really expand the model to include many more variables. So include variables relevant to other physical processes and also at various levels in the atmosphere. So expanding the data set by probably 1 or 2 orders of magnitude. So some of the key scaling challenges in this model are that basically the 2 big ones are FFTs and large matrix multiplications. And I want to spend a minute here describing what the challenges are. I won't be able to, obviously get into the full details of the complexity and parameter count and so on, but you'll have to take my word for this and go check it out in the paper. So basically the 2 main things are dealing with large FFTs. So we have to do FFTs on the data set. Right now we're working with 25-kilometer data, which corresponds to basically images of the size 720 by 1440, so about 1 million pixels. And we have D of these, and that's actually quite important. So D is the embedding dimension. In our case, it's about 1,024. So we have 1,024 such FFTs across all the different channels. Now, when we look at 5-kilometer data, which is sort of our next step, we're looking at basically a 25 times increase in the size of the FFT. So we're looking at very large FFTs. And once again, D of them and this embedding dimension would be even larger for 5-kilometer. And finally, sort of the holy grail is to get to 1 kilometer. And that would be essentially FFTs that are extremely large. So distributed FFTs across GPU multi-node becomes really important. And it's quite exciting that the new technologies that are coming up with NVLink and large communication for the new GPUs enables us to do basically very large FFTs very efficiently. The second challenge is matrix multiplication. So here we have, of course, in these networks, very large matrices and many such matrices. In this case, the dimensionality is about 4D by D. Once again, D is about 1,000. And we have N of them. So N is the size of the sequence in this transformer model. And that actually scales as the dimensionality of the data. So this is often of the size of approximately 1 million for the 25-kilometer model, 25 million for the 5-kilometer model, and 625 million for the 1-kilometer model. So we're looking at basically very large matrix multiplies and many of them. So once again, GPUs are well suited for this, and there's techniques to optimize this as well. So one of the nice things about this approach is that scalability is quite promising for the network architecture. So putting it all together, this sort of one slide captures basically the whole process. We have data coming in from multiple different sources. In this case, the reanalysis data set, which combines observations and numerical simulations. That's used to train a model using FourCastNet in this case to build an AI emulator. And that emulator can be used to make all kinds of predictions, evaluate impacts, mitigate disasters, characterize extremes, and so on. So this is sort of the pipeline that we envision for building a digital twin. And of course, this is iterative. So as new data comes in, we continue to calibrate and predict. On the bottom gives you a sense of the current data sizes and the time that it takes to train. And then the future data sizes, looking at the sort of the next step of 5-kilometer resolution. So this is stuff that I've already described. So we're looking at now, currently the model has 20 variables. It's about 10 terabytes of data at 30-kilometer spatial resolution and 5 different levels in the atmosphere. Looking ahead, we're looking at future data that is of the order of about 10 petabytes coming from 5-kilometer simulations at about 20 different vertical levels and 300 variables. The current training time is about 16 hours on 128 GPUs. And of course, this decreases as we scale it out to a larger number of GPUs with model and data parallelism. But the inference is extremely fast, about 1/4 of a second for a 7-day forecast for a single member. And projecting out into the future with some sort of basic models that we have, not quite SOL analysis, but projections are that we are looking at 200 hours of training time on about 16,000 GPUs for the 5-kilometer model. But the great thing is that the inference can still be very fast. So we can still have basically large ensembles created in a few seconds or a few minutes. Of course, the implications are many, and we've already talked about it. There's lots you can do with this sort of model in terms of characterizing extremes and predicting impacts and so on. So here we are today. We have unprecedented skill on certain variables at short timescales. We can produce large ensembles in a few seconds. We're 4 to 5 orders of magnitude faster than NWP and four orders of magnitude smaller in terms of energy footprint. But really, I think a lot of the exciting challenges lie ahead in terms of embedding physics constraints into the model to make it physically consistent, to make it causal, and also to extrapolate to new scenarios, expanding the full state vector, so capturing variables corresponding to basically the entire global weather and climate system. Moving to higher resolutions, there's data on hand for 9 kilometers, even 5 kilometer and 1 kilometer data sets are being created as we speak. So pushing the model to even higher resolutions is really important. And part of that is using clever methods to capture the fine scales, like using generative models, GANs or diffusion models, or various other approaches to characterize the fine scales more accurately. Uncertainty calibration is something that we're working on actively. And one of the things that we are leaning heavily on from the domain experts is really being able to develop a suite of diagnostics to evaluate the performance of the model. Obviously, weather and climate modeling has been around for a long time, and there's lots of diagnostics that are used to evaluate the performance of the model. But I think data-driven models at this point in time really need to be pushing in that direction in terms of really characterizing the performance in terms of the physics and impacts. Of course, we're now at weather timescales, but we care about climate change, so we need to push the model out to longer timescale predictions, and finally also use machine learning approaches that are being developed for data assimilation. So I want to maybe mention one idea that was brought up by Bjorn Stevens in his keynote at GTC recently, which I think is really exciting in terms of thinking about how, even if we don't have very long predictions from data-driven models, how we can couple them with numerical models to really be able to characterize these long trajectories of climate change. So let's imagine here basically a numerical climate model like COSMO or ICON or IFS, and we have basically a trajectory that's calculated out to something like 300 years. So this is a standard climate simulation going out to very long durations. Now, this is typically obviously what's done in climate modeling. And if we think about a 1 kilometer model, it would be a tera-dimensional phase space. And maybe the most important point to make here is that having a 1 kilometer climate model that's dumping data every 30 minutes or so gives you an exabyte of data over this trajectory. So the implications are that you can compute these, but you can't extract the information because of just the scale of the data, leave alone interacting with the data. So how can a digital twin like what we have now help really achieve that interactivity and extraction of data? So here is one approach to do that. So you take the same model and you predict using your numerical model this 300-year trajectory, but you checkpoint the model and only write out data once in 30 days. So you only have very few checkpoints every 30 days. And these checkpoints can be used to initialize a data-driven model and explore all possible trajectories around this particular checkpoint. So essentially, you've decreased the amount of data that's being written out by orders of magnitude, but you've also enabled a data-driven model to explore the surrounding sort of phase space out here. So this is one way in which I think coupling a data-driven model with a numerical model can be very powerful, even before data-driven models can really predict very long-term climate change and extrapolate out. So there's some very promising approaches. And the other nice thing about this is that you might, as your data-driven model increases in its skill and improves predictions, you might only checkpoint once in 60 days or maybe once in a year. And that way you basically can continuously decrease the load on the numerical model and increase the load on sort of the data-driven model. So this, I think, is a promising approach. And with that, I just want to synthesize briefly what we discussed, which is the need for extreme scale computations in climate modeling remains and continues to grow with increasing resolution, larger ensembles, and more scenarios. At this particular unique time in computer science and computing and AI, we have some really exciting ways in which we could achieve these million-x speedups. And Earth-2 is the project that's trying to utilize all of these technologies to essentially provide digital twins that can be used for predicting climate change and having actionable results in actionable time. Okay, so that was 45 minutes. So I will pause there and thank you for your attention and happy to take any questions.
Before we move to Q&A, just a brief announcement. Our next SPCL Bcast will be in 2 weeks on the 21st of April at 9 a.m. Zurich time. So fairly late if you're on the West Coast. At a nice time if you're joining us from Tokyo. We'll have Geronimo Castrillon from TU Dresden discussing language and compiler research for heterogeneous emerging computing systems.